Greetings to everyone. I'm Will Gosnold. I'm at the University of North Dakota. Today I'm going to be talking about some things I've worked on for quite a long time, and they're all related: heat flow, climate change, and geothermal energy. So here's the outline of my talk. I'm going to ask a question right off the beginning. Do we need to correct the temperature gradient for climate change? After I cover a number of things, we're going to come back to that, and you're going to see what kind of information I've been looking at, and I would like to ask what you think about it. So then we'll go to climate change. One of the things is when we began using borehole paleoclimatology to try to work out what's been going on in the past, we didn't really know that much about how climate changes. So I'm going to cover that very briefly. And I'll look in depth a bit at the last 21,000 years to present. Then I'm going to look into how we go about using borehole temperatures to extract the climate and how I've been doing that and how I've been finding some very interesting things. And then I'll come back to the question, do we need to correct our data? Then I will close with a different perspective, and that is, can we use what we've learned from borehole paleoclimatology for geothermal exploration? So let's jump into the climate change system. One thing you may not know is that the solar radiation falling on the planet has increased since the formation of the planet by about 27%. That is a great increase, but that's over the last 4.5 billion years. We can cut this down to the last 300 million years, and we get into what is known as the Blagg hypothesis, named after its creators, Berner, Lasaga, and Garrels. This is due to plate tectonics. If we go back 300 million years, the planet was really cool, but then we went from what was pretty much of an ice house to a greenhouse planet overall. This is because increasing speed of plate tectonics through more CO2 from volcanic eruptions into the atmosphere. In fact, the amount of CO2 in the atmosphere at the end of the Cretaceous was several hundred times or greater than what it is today. And it created that. And then the plate tectonic motions began to slow down, and the planet got colder as the CO2 was taken up. Then we cut that down to orbital things, the Milankovitch cycles. These are glaciations during the last 3 million years. The last four, as you can see here, were much larger and a lot longer in time. They were lasting each about 100,000 years. Then we cut down to the last 50,000 years, and you can see here we're coming out of the last glaciation, suddenly getting warm. We'll look at this and we do the last 21,000 years, and then we get into the record where people are around and we're recording what was going on. So a quick look at the orbital causes of climate change, dealing with the Milankovitch cycles. On the right, you see the elliptical path of the Earth about the sun. We have a perihelion, which is its closest point to the sun, and we have the aphelion, the farthest point. This year, the closest point occurred on January 3rd. The source I got this from had it back around December 21st. It's moving. That is, the ellipse changes in our cycles. But if you go through the complete cycle, you can see by 11,500 years from now, the perihelion is going to be on June 21st, which means that's going to be a pretty hot summer. And this is a 23,000 year cycle. The tilt cycle is 41,000 years. Their rotational axis has a maximum tilt of about 24.5. Right now we're at about 23.44, and there's a minimum tilt. This changes over time, and like over here, we get a precession over here. This axis wobbles a bit like that, and you put all that together, we get a 41,000 year cycle. But that controls the amount of sun that's falling on the planet's surface. Well, one thing we know about all this is the temperature of the planet is controlled by solar radiation. And without the greenhouse gases, our temperature would be minus 16 degrees C. This is the average over the planet, not plus 15 degrees, which it is right now. The greenhouse gases make a lot of difference. The major ones, of course, are water vapor, carbon dioxide, and methane. The anthropogenic ones that have been increasing, carbon dioxide and methane, are of extreme concern. Now, there are other greenhouse gases, and I've just listed a few. Again, the major one is water vapor, which pretty much is constant. It doesn't get greater and it doesn't get less. But carbon dioxide, methane, and these other anthropogenic greenhouse gases do. And we can look at the numbers. In 1750, which was pretty much considered to be the onset of the industrial age, the CO2 content was about 280 parts per million. Today, it's 430 parts per million. Methane, 700 to 1800 at the beginning of the industrial age. Now it's 1912, and it is 80 times more effective in raising the temperature than carbon dioxide. Well, let's move on and look at the last 21,000 years. So diagram, and I'm going to show you this. This is a plot of CO2, winter insolation, summer insolation, and ice on the planet compared to what's today. If you can see this white line in here, this is today's condition. So what do we have? If we go back to 21,000 years ago, the CO2 was 90 parts per million less than it was in 1750. The ice sheets were at their maximum size. Sea level was 116 meters lower. There's a lot of land exposed. The insulation at that time was pretty close to what we have today. We jump forward 11,500 years. CO2 gets to the present level. Notice it goes along to here. Here's the winter insolation. We're getting to a point where that was a minimum. It's almost 20% less. Summer, much, much greater. And it was melting all of the ice on the planet. It was disappearing quite fast. Today, CO2, 430 parts per million. This is measured at Mauna Loa Observatory, which has been going on for quite a long time. The global temperature is now 1.5 degrees C above what it was in 1750. And other things obviously are happening. And how do we know this? Well, the geologic record has all of this. We have a lot of information from geology that tells us what's happening. Now, there are other ways of looking back into the past that have been going on. Tree rings, these upper two panels right here, are a proxy sensor of what the temperature was in the past. It was very controversial for a while. Several people have been involved in this, and they pretty much agree that's what's been happening. Other places, we get it from the ice. This is from the oxygen isotopes, and we get it from caves, again, oxygen isotopes. And there are many proxy systems that have been used over time, just quite a few. But only one actually measures temperature. It's not a proxy system, and that is the boreholes. And we're going to look into that. We do have some atmospheric temperature data I wanted to show you. This is global land and ocean put together. The way this has worked is to simply take the average of all the data, subtract it from what it is, and then you can see if it's below, as we are here, it was colder. We go through a period, and then we suddenly get a grand warming, as you see along here. Another way of looking at this is to looking at the seasonal temperatures. This goes from January to December, and this is from 1880 to 2023. So as we're going up in the summertime, for example, we go from cold to warmer and warmer. In 2023, instead of the temperature changing by a bare tenth of a degree C, or even a few hundredths of tenths of a degree, it jumped up to almost a degree. This has the climate change community very concerned. Well, let's go back to the borehole paleoclimatology and take a look at it. A couple of things I would point out. The paper in 1986 by Art Luckenbrook and Vance Marshall. It was published in Science, looking at the permafrost in the Alaskan Arctic. And then, as we began doing a lot of work on paleoclimatology, Henry Pollock and two of his PhD students at the University of Michigan put together this diagram we see. This is the borehole paleontology signal. Of course, the error gets larger as you go back in the past. The blue is the atmospheric temperature and showing how they path together. And then a very interesting one that came up, and we'll do a bit with this. Vladimir Chermak logged boreholes in southern Canada, here in Ontario. You can see the sites up here. Three of the sites at Kapuskasing, Cochrane, which you will see several more logs of, and Hearst. And you can see the warming in the ground up here. Rather interesting. Well, I followed that up in a sense. I went into Minnesota in collaboration with the Geological Survey of Minnesota, especially with the people at the University of Minnesota Duluth and here, and we recorded 30 borehole temperature profiles, and this is the borehole temperature profiles. Looking at this, you can see that, in fact, it's a lot different from what we saw with Vladimir Chermak's. So I would ask you, why do you think that is? Well, we could take a look. Here's his original profiles. This is what we see in Minnesota. Why aren't these curves like that? Because it's been warming up for 51 years since Vladimir logged these wells. If you go back, you're going to find that they've moved over. And in fact, we will get to do that as we go along. Well, jumping back a little bit, how do we know what's been going on? Well, people have come up with a number of schemes to look at the borehole data. This is 5 of the logs from Minnesota. They have different microclimates, by the way, different surface temperature intercepts like that, but they're all separate and they have pretty much parallel curves. So what do? We ask a question, what has the surface temperature been doing over time to create these profiles? So this is the functional space inversion scheme worked out by Xiaopeng Wang and Po Shen with Henry Pollock at the University of Michigan. So I inverted all 5 of these holes, and I got different answers for each one. Why? Different microclimates, different ground covers, and they give us a different answer. It could be a little frustrating. You can say, well, I can see it here, but why don't I get the same picture? It's because every borehole is slightly different, but its surface has a lot to do with that. Now, here's another way we could look at it, and that is to ask the question, okay, are we seeing the air temperature? Or are we seeing something else? Well, I have a computer program that I use. This is a 3D version of it, as you're seeing. I control the surface temperature, and then I let every cell underneath this interact with every other cell with just heat conduction, heat flowing from one cell to the next. I use a temperature input, and this is the temperature input monthly data for a climate station. And you can see summertime, wintertime, and so on like that. And I let it run, taking each point, each month in this case. I also do it on daily, weekly, or annual basis. But we control the temperature at the surface. For every time step, the temperature changes. And this is a map of what's going on in the subsurface in color. So we're starting back here at 1915, cold times, and you can see there are warm pulses coming along like so. Even a nice, I think this was 1950 when we had a really, really cold year, and it kind of hung over as well. But you know, since I record it like this, I can draw a line across here, and I can get the temperature of the ground subsurface at any time, or I can draw straight down and get a temperature profile in that, and it changes over time. Now, I did this also in another way. This is an area in the mid-continent of North America. This is Canada up here, North Dakota, South Dakota, Nebraska, and Kansas. The red dots are boreholes where I measured temperature profiles, and they're listed for several of the places over here. And the green squares are climate stations. So I put together, made a model climate station. And this was done in 2004. And then I also took the borehole data from these sites and plotted them on here. So this is the temperature change recorded by the borehole from no change, like right this. And you can see the air temperature pretty much parallels what the boreholes are doing, or the boreholes are paralleling that. Look at another group just going to South Dakota. You can see the same thing going on. Again, these are boreholes that I did. This is the model from the temperature from the climate stations. And I put this together going all the way down to Texas, in fact, using models and so on. And this is, by the way, the change. And this is comparing the observed data from the boreholes to the modeled from the air temperature. In fact, they compare pretty well, although in Canada, the change has been even greater. So the question I'd ask was, are we modeling the air temperature? Are we detecting the air temperature? Or is it possibly something else? And this was like, yeah, we're getting something from the air temperature. But is it? Well, I want to look at a time series on this and see how it goes. So this is air temperature data again. And you would ask, is there a trend? Well, if you try to fit a curve to that, you would say, no, the interannual variability is so great that we could never accept or reject the null hypothesis. There is no trend. But if you can do what I just did with that time series of changing and modeling the subsurface, we'll see something else. So here we are. Here's the air temperature. And then we're going to look at 5 meters, 10, 15, and 20 meters, and they're all plotted in here. But if we separate them, we'll change the scale from 30 to minus 30 to 6 to minus 4, only 10 degrees. And suddenly you see a slope. And not only that, the correlation coefficient gets high enough that you're saying, yeah, we can mathematically say and statistically say it is changing. Drop down to 10 meters, 2.5 degrees to minus 1 degrees. 15 degrees, you see it changing again. We're only looking at basically about 1.2 degree on the vertical scale. But the ground is filtering out the high frequency signals, and we're getting a really good look at it. Notice the correlation coefficient is up here. 90% of data is variable. Now I'm going to look at another region. This is where I drilled, or had drilled, 5 heat flow holes to look for geothermal energy. And as a concept, this is across what's known as the Williston Basin. It's deeper out here, much deeper farther to the south. It's shallow up here. And we thought we were going to see groundwater flow carrying heat up through here. And in fact, we did. But looking at this, I thought it's really great. I went out looking for heat flow and I found that. But then about, 2005, I got an email from Vladimir Chermak, and he was coming to the U.S. and he wanted to come out and see if we could go relog our boreholes. And I thought, well, that'll be interesting. We're not going to see anything, but it'll be a nice adventure to do that. So this is what the surface looks like. A couple of my former grad students, pretty much the same time, different areas. And here's what happened when Vladimir came. This is the Minot hole. This is the Landa hole. This was the farther one to the north. They were logged at 10-meter intervals in 1984. You can see this in both of them. Then Vlad came, and that's what we saw. I started going back, 2002, 2009, 2011. I continued this up through the early 2020s, but then due to the oil boom in the Williston Basin in North Dakota, all of these holes got destroyed by rebuilding the roads. But this is an amazing picture of what was been going on in the past. Now, an interesting point. If I view this at the scale we originally logged, and I had gone back and logged the holes the same way, I might have missed the signal because I would have seen some variability which I wouldn't be sure about. But it's changed everything we do. I go back to, I didn't mean to jump to this, I'll come back to it. And I see I'm not going to be able to get this thing to go backwards for me. And I do not know why. All right, we jumped past a few things. We're looking at something we did not have in the past. We have a system of temperature logs and climate stations throughout the entire state. The North Dakota Agricultural Weather Network, it's called NDAWN, records data. They record air temperature, turf soil temperature, and bare soil temperature. And what I've plotted here is for Bowman, North Dakota. This is in the southwest corner of the state. The air temperature, as you can see, and this is the soil temperature recorded at the same site, same time of day, and so on like that. And notice they are very different. Which one of these signals goes into the ground that we're measuring with our borehole temperatures? It's not the air. This is the Grand Forks site. It's a longer time period. The other one is just 1993 to present. This is 1990 to present. So we have much more data, but you see the same picture. Now, an interesting thing about this, and you may see a little bit of it in here, and that is that this is the Bowman site. Notice the temperature goes below zero, and so on like that. But then you suddenly get to a place out here where the temperature doesn't seem to go below zero. That's even more pronounced in Grand Forks because we went from a drought period in here to suddenly high precipitation. So the soil is frozen as you go into the freezing signal, and the temperature of the ground surface never gets below zero. So are we really measuring the air temperature change? Yes, but we're measuring really the soil temperature change. The average air temperature in Grand Forks over this time, 4.9 degrees. It's almost twice as high for the soil, 18.15. That's what we're seeing. What's in the soil, not what's in the air. So, and again, I just want to emphasize drought period, high precipitation, and how that went. So, do we need to correct the data? I'm going to ask you a few points about that. We have ensembles of heat flow determinations from actually all over the globe, but I'm going to compare Eurasia and North America. It increases with depth, and we see temperature profiles in deep hole boreholes do show increases in heat flow with depth, but it's a very subtle signal. Actually, the post-glacial warming might have been much, much larger. And unfortunately, most of the boreholes we use for heat flow are not deep enough because they all have this anthropogenic warming signal. So a few plots. This is just the International Heat Flow Commission's borehole data from about 2000. And I plotted it like so. And yes, there is a slope to it. This is North America. There is a slope to it. So let's compare all of these. Europe, Russia, China, and North America. The total data here, the number that are actually deeper than 2 kilometers that get beyond the last glaciation. And the number of data that are actually greater than 60 milliwatts per meter squared. Why is this? Because that profile is curved and it causes a reduction in the gradient and what we see in heat flow. So I want to show a little more on that. Going back to Canada with Shannon and Rachel, a couple of my undergraduate students. In 2005, Alan Jessup in Calgary, Alberta, called and said, would you like to go log those boreholes that Vladimir logged and see what they look like today? We did. We couldn't find them all, but we found something very interesting when we did this. So what's different? This is the same place. This is in Cochrane, Ontario. What do you think is different from today to back when Vlad logged the holes 51 years ago? Well, I'm going to give you an example of that. Here's a forest, steady state temperature gradient, nice linear temperature profile. But what if we have a forest fire, or if people move in and take the forest away for cropland? Well, we can model this using my temperature modeling system. I just let this burn down 1,000 years ago, and I'm modeling the temperature scales. And I can plot a profile 500 meters into the clearing, 500 meters into the forest, and then closer and closer to the edge. And here's what we get. Again, putting the diagram up here. This is 500 meters into the clearing. And now this is the disturbance. It's not the temperature profile, but the disturbance to the profile. The 2 degree C difference is about the average we got from all that data in Minnesota, forest versus clearing. And notice, even in the deep forest, there's a disturbance to the temperature gradient because of the change in the land surface. This is important. And here's what we got from the data. Here's the Cochrane heat flow site. This is Vladimir Chermak's log. This is what Ellen Jessup and I logged in 2001. Here's what Shannon and Rachel got in 2005. This is modeled using the climate data, and it didn't turn out the way we expected it to. This is the climate data from Kappa's casing. It goes from 1919 to 1999. And notice this moves around. It was colder in older times. And again, this is going towards zero. You take the actual gradient out, so you're dealing with what if there was no change. But we go around to 1999, and you've got this huge climate signal that you see here. We couldn't find the Kappa's casing hole. Ellen and I looked, and Shannon and Rachel and I looked. We just simply couldn't find it. Now, I went to a meeting in Germany some time ago, and one of the scientists there walked up and he says, "So, what are you doing about the glacial signal?" I said, "Oh, I'm ignoring it because Francis Birch said it didn't matter." He says, "Well, let me show you something." And he showed me this. And I looked at it and I said, "Oh, wow, we're going to have to do something with this when this gets to, do we need to make a difference?" Well, yes, we do. Now I have a data set that's really interesting in this regard. This is a proxy temperature record from Manitoba. It's the May, June, July, and August temperature record based on pollen analyses in upland lakes. C.J. Ritchie published this in 1983. So we come out to 12,500 years ago. The ice is present. The ground surface temperature is zero. And then over time, it changes like this. Well, can I model this? Well, I can't just use the May, June, and July temperature, but I can use the annual temperature. Fortunately, Winnipeg, Manitoba has a temperature record that I can use to scale this back to get the annual temperature changed. And you see, again, from zero, we'll go up to about 9 degrees above present. And then in about 2,000, more than 2,000 years ago, it drops back down to here. So what I did is I took this, and every 500 years, I plotted a new curve. Well, here's the zero curve here. This is after 500 years, 1,000 years, 1,500 years, 2,000 years, and so on, until we get to this point out here. And then it starts cooling back, and you can drop down, and these are the profiles in here. And then when you take that and add it to an undisturbed, let's just say we had an undisturbed geothermal gradient, this gradient over here, this is the curve you get. I did put in the anthropogenic change up here, but the separation between this curve and this curve is the post-glacial warming signal. And I certainly do think this is a factor. This gives you a lower heat flow than this does. And this time when we were dealing with climate change, I remember talking to John Sass. John says, "I don't see it. We logged maybe a 3-kilometer deep borehole in Flin Flon, Manitoba, up in central Manitoba, and we didn't see any climate change." Why not? Because this is what happened. It wasn't a step function that went up here and stayed this way. It was a very complex function like so. Does this happen in other parts of the globe? I think we ought to look at it. So let's change points. I'm going to see if we can actually do this, turn this around and say, can I get a geothermal gradient that's useful from a very shallow well? Well, that's for geothermal exploration. Well, I was sitting in my office about, 10 years ago, oh no, 7 years ago, and the phone rang. And it was a scientist from the University of South Carolina, and he says, I have a question for you. Can I actually get a good geothermal gradient from a 5 or 10 meter borehole? And I had answered the phone. Normally I ignore phone calls from elsewhere, but I don't know why I just picked this one up. And I said, you know what? If you had called me 2 years ago, I would have just hung up the phone. I would not have answered because that question would have been ridiculous. But it turns out a couple of years ago, I had a couple of graduate students, and for our heat flow project in my heat flow class, I said, let's look at what's going on with the Mars data. That is the Mars Rover Experimental Monitoring Station, as they call it, the REMS temperature data. Well, we had 3 years of SOLS data, that is the daily temperatures from Mars. And this is the maximum soil and air plot. This is the max or average soil and air plot, minimum soil and air plot. Which one's warmer? The soil, just like we saw in the work that has been done by Endon. And I realized what we had. Well, at the time, there had also been a NASA scientist who came to UND and gave us an interesting talk on the InSight rover and what they were going to do. So what they were planned to do with the InSight rover, they're going to put in 2 instruments. One would be a passive seismometer, and the other one would simply be a heat flow probe, 5 meters deep. And that's why I looked into this. I said, geez, can they get that? Is there a climate signal on Mars? Well, yes, there is. So we worked this out, and I said, well, geez, can they get that? Well, at the time, I don't think they could have because they weren't looking at the climate. But if you could actually model the climate and see what its impact on the subsurface temperature would be, yeah, you could subtract that from the gradient you measure. So several people have looked at this. This is basically what they were going to do. They were just going to say, all right, if there's climate, we can model it like that. We've all done this exercise probably, so we know what's happening. But is it really climate? Well, here's what the InSight probe data are. So I took that and modeled that going into the ground, and you see it's quite complex. At 5 meters, boy, it's going to be really tough to do that. But you go from 10 to 5, and yeah, you're probably getting something that you can actually do something with. If they were just going to 5 meters, this is a plot of the actual temperature over time. The numbers here are the number of sols, and as you see, we go along. This is the gradient at 5 meters below the ground. You see it's going all over the place. So yes, you've really got to take that signal out. Well, what did I decide to do with the guys from South Dakota or South Carolina? Well, we happen to have a climate station with a borehole. So we have a climate station like this. Well, unfortunately, it's no longer active, but there's a number of other climate stations. That is, those climate stations that the Endon people have all over the state. And we can look at that. So we were out there logging that borehole. This is a set of logs from 1992 to 1993. I logged just about every month in there, and you can see the signals going around. Notice how smooth they are. And then I started taking students from my classes and so on. This is from one of my undergraduate classes, and we had plenty of time, did a good job. And these are graduate student logs. And this is the group of graduate students. And as you can see, we can understand why those logs are crooked and kind of wobble. These folks are not accustomed to the North Dakota weather, and they came out not dressed for what they were facing. Well, we went ahead and logged the hole. They started out, in this case, dropping the probe too fast. In this one, they sort of dropped the probe too fast as well. But we get around that now. We log and do it a lot slower. This past summer, we logged the borehole. We got in several really good logs. This is what it looked like on May 13th, which is the first day we could get in the hole. The reason is it was iced in. We had to wait till the ice melted and so on. July 1st, this is what it looked like. And I just thought I would throw in a little humor in this. Don't go into the long grass. You know, that quote's from Jurassic Park 2. So here are the plots we got from that. May 13th, July 1st, July 27th, September 1st. And I plotted a different scale. One thing you can see in this, that it's curved like this. This is the anthropogenic warming that's in the signal. So that's there. Is there any trace of post-glacial warming? Well, yes, actually there is. So how can we do this? What we're going to have to do is remove all climate signals, get as much climate data as we can, and see if we can pull it out that way. An example of what we're going to try to do out in the western U.S. is, imagine this. If you're looking for something, if you drilled a series of holes, 100 to 200 meters or so like that, it's pretty expensive. But if you could do this with a 5 to 10 meter hole and come up with the same answer, and you're trying to find something like this is a hot spring, and you want to know what's going on, which way is the fault that goes in there? You could put in a 5 to 10 meter pattern around this and come up with a map of what's in the subsurface. And if you're trying to find the fault, imagine this is what's going on with the subsurface, and then you have different temperature profiles in different places. This is distance from the fault, but if you had a map pattern, you could come up with the answers. And just to remind you again, the signal changes with depth. And so I'll close with a picture. I'll say, yes, we're going to be able to do this. And a picture of one of Vladimir Chermak's very famous meetings in Czechia for the heat flow scientists.